start now.
Awesome. All righty. Well, thank you guys for all coming to listen to my presentation today. My name is Blake Busby, and I'm going to be presenting on the topic I did for GIST 909, which is monitoring the mega drought and the effects it has on reservoirs in Southwest Colorado using a change detection analysis. Before we get into this project, I think it's important to understand what a mega drought is. And the Western United States is experiencing the longest drought in the last 1,500 years and is referred to the mega drought, which is any drought that lasts over 20 years or more. And currently this mega drought's been going on for 22 years. And the Western United States has experienced below average precipitation and above average temperatures, mainly due to climate change. And a lot of the mainstream discussion is focused on the largest reservoirs in the West, Lake Powell and Lake Mead. And mainly the reason for this is, again, they're the largest and they provide water for about 30 to 40 million people. That said, Lake Mead and Lake Powell are just still a part of the Colorado Rivershed, and to further understand the implications of the current mega drought, further research is needed on other reservoirs in this watershed. So to do that, I selected 3 reservoirs of interest: McPhee Reservoir, Vallecito Reservoir, and Lemon Reservoir. All 3 of these reservoirs are located in Southwest Colorado. McPhee Reservoir is the largest, followed by Vallecito Reservoir and Lemon Reservoir. And these reservoirs were initially created to control the spring runoff from snowmelt in the mountains, but it was also created to provide water for farmland and livestock, as well as drinking water for nearby towns and cities. And McPhee is created as a result of damming the Dolores River. Vallecito is created as a result of damming the Los Pinos River. And Lemon Reservoir is created from the result of damming the Florida River. So just a quick photo before we really dive in. This is what McPhee Reservoir looked like in June of 2021 from the west end. You can see the water line on the rocks in the back and where the water is now. And I think it's a pretty dramatic photo to start with. So let's talk about the data that was used in this project. It's composed just of 2 types of data, raster and vector data. The raster data in this project comes from Landsat 8 images, which were downloaded from the USGS Earth Explorer website. And a total of 9 scenes were downloaded, 1 for every year from the period of 2013 to 2021. And these data had, or collection 2, level 2, which were selected because they have pre-computed reflectance values, which would just save time on processing and storage space. The vector data used in this project was produced by Esri Data and Maps and is available from ArcGIS Online. And this vector file that was used is just displaying all water bodies in the United States. And it was used so we could get the perimeters for the 3 reservoirs of interest. Of course, before the data could really be used to perform a change detection, some pre-processing steps were needed. To do this, 2 models were built to automate the pre-processing steps and ensure the repeatability of this project. So what the first model did was put the data into the appropriate coordinate system, which was UTM zone 13 in. Then the model identified the reservoirs of interest, and then it extracted the satellite scenes to these reservoirs, again, just to save on storage and pre-processing steps, or processing speed. The second model applied the scaling factor to the Landsat 8 images to convert them out of their digital number format. And here we'll see just the first model with all the Landsat images going into the batch project raster to project into the appropriate coordinate system. Then down below, you can see the study lakes going into the project coordinate system and the select layer by attribute, and then that being used as the mask for the batch extract by mask tool. Let's talk about the data processing. 2 models, again, were also built to process the data. The first model did was create an image cube. And so the first step of the model was to compute the normalized difference water indice, or NDWI, which is when you take band 3, the green band from Landsat 8, and subtract band 5, the near infrared band, and then divide that by the product, or by adding band 5 to band 3 again. And then all of those NDWIs were added to a mosaic data set. And then multi-dimensional raster was built. And then that raster was copied to the cloud raster format, or .crf, which is kind of Esri's or ArcGIS's preferred file format for working with multi-dimensional rasters. Then what the second model did was built to produce the change detection raster by using the analyze change using land trender tool and detect changes using the change analysis tool. And we'll look at those models here. So you can see Landsat bands 3 and 5 going into a raster calculator to compute the NDWIs for the steps, or to create the NDWI for every year, which created 9 total. And then they're going into a mosaic data set, and then the build multidimensional info tool was used to add the image acquisition date as well as the NDWI values into this multidimensional raster. And then it was copied to that and producing the Landsat time series CRF, which was then used for the second model, which was the one built to detect and analyze changes within the image cube. So you can see that that same CRF file goes in and to the analyze changes using land trender tool, and then that output is used as the input for detect change using change analysis raster. So now we'll talk about how the results of this were quantified. So one way is a model was built to quantify these results. What the model did was create random points that were used to sample each of the NDWIs that were created. So each of the 3 reservoirs got 500 sample points for a total of 1,500 sample points. And then, so there was 1,500 sample points for every NDWI. What then happened was the values were extracted using the extract multi-values to points tool, and then the table to Excel tool was used to export that table to Excel. And then once in Excel, different metrics were used to quantify the results, and we'll just briefly cover some of them here. So again, here's the model showing the study lakes going into the create random points tool, producing the NDWI sample points feature, which then went in along with all of the NDWIs to the extract multi-values to points tool. And then all of that data was exported Excel using the table to Excel. So now we can talk about the results for all sampled pixels. So this table and graph is showing the average of all 1,500 NDWI points for the 3 reservoirs. So just looking at the 3 reservoirs on a yearly basis. And it's kind of, I think, important to start at the beginning, because if you see the reservoirs in 2013 started off relatively low, and that NDWI value actually registers on the scale as a moderate drought. But then in 2014 and 2015, values did increase to where they rose to their highest in 2016, which average pixel value of roughly 0.5. But then over 2017 and 2018, the values kind of took a pretty large dip, and then where they rose again in 2019 and then decreased all the way to 2021, where they registered their lowest values, which the NDWI scale classifies as a moderate drought as well. So now this is looking at the average value of sampled pixels in the 3 reservoirs. So this is splitting those averages up, and now looking at it on an individual reservoir basis. So each NDWI, or each reservoir, has 500 points. And again, looking at McPhee, because like I said, it is the largest reservoir, it did start with the highest average NDWI value. Kind of followed that trend there where it rose actually quite a bit in 2014, and then to its highest value again in 2016, and then decreased for 2 years, and then had an uptick in 2019, and then falling again to its lowest value in 2021. As for Vallecito Reservoir, it didn't take as large of an increase in the first year, or 2013 to 2014, and actually decreased in 2015. It did still hit its highest average NDWI value in 2016. And then again, it hit its lowest average NDWI value in 2021. Now for Lemon Reservoir, which had the lowest starting NDWI value, that was classified as a moderate drought from the beginning. It did increase in 2014, and then it rose to its highest in 2016. And then again, this reservoir also registered its average or lowest average NDWI values in 2021. And now we can kind of look at a map that was made displaying all of the NDWIs for each of the reservoirs for each year. So something to note about these 2 reservoirs is the dams for them are both located on the southern portions of these reservoirs, and these maps are north facing. So a lot of the change that you can see in these reservoirs, you will notice from the north end. And so just looking at these, it's kind of interesting to see 2016, which we know both of these reservoirs registered their highest average NDWI values. and then in 2021, directly below it, where both of these reservoirs averaged their lowest NDWI values. Now, this is an NDWI looking at McPhee Reservoir, and the dam for this reservoir is actually in the northeastern portion here, or sorry, northwestern portion of this reservoir. So a lot of the changes that you can see happen in the southern part. Again, McPhee also registered those highest average NDWI values in 2016 and its lowest average values in 2021. And looking at those two images there, you can really see a pretty large change. And next here is actually a time series of McPhee Reservoir. And we'll just play it. It's only about 40 seconds long. And you can see the reservoir starting off relatively low. And then in 2014, of course, it increased. And then in 2015 as well. And then we know 2016 was the year it registered the highest average NDWI values. And then in 2017, it decreased. And then in 2018, it decreased. And then we'll know next year in 2019, it actually increased slightly. There we go. And then for the next 2 years, it decreased to its lowest level or lowest average NDWI points throughout the study. There we go. And the darker blue is registering higher NDWI values, while the white is registering low NDWI values. Oh, sorry. So for the discussion of this project, so it's clear from those two tables that in 2016, all reservoirs registered their highest average NDWI values. And in 2021, all reservoirs registered their lowest average NDWI values. So looking at those graphs and data, the reservoir started off relatively low and actually filled up quite a bit in 2016. But even with some upticks like in the year 2019, they still were falling very quickly. And snowpack is known to be the main indicator of these reservoirs' NDWI values. But another interesting thing that isn't always discussed with these reservoirs in the Western United States is how seasonal rain or the lack of can also have an impact. Also, above average spring temperatures can have an influence on NDWI values because this can cause a premature release of the water from the snowpack. So let's talk about snowpack and NDWI values. So for this study, some auxiliary data provided from the NRCS, the National Resource Conservation Service, was used. And so for the snowpack remaining in June for the years NDWI was calculated, appears to have a pretty large impact on the values. For what this means is if the June snowpack was higher than average, the reservoirs all registered an increase in NDWI values. So if the remaining snowpack in June was above 100%, the reservoirs would register an increase, which that's to say just because the snowpack remaining in June doesn't mean that the overall yearly snowpack was above normal. And some future research for this that I think would benefit this project is additional years of data, past and future. So going back in time to see if 2013 was just one of those abnormally dry years and the water, the reservoirs would average higher NDWI values. And then of course the future to see where these reservoirs are going and what's going to happen. I also think this research could be attempted maybe at a different time of the year, maybe such as the fall after all the snowpack is gone, and maybe after the seasonal late summer rains which affect this area come in. And I think we'll end this project with a pretty interesting quote, which is years of drought and famine come and years of flood and famine come, and the climate has not changed with dance, libation, or prayer, which was said by John Wesley Powell, who is the former head of USGS and who Sig Powell is named after. Thank you guys for tuning into my presentation, and I guess we'll do the question portion.